We now continue with a look at the difference quotient. So suppose you have some function f of x and you want to know the gradient of a secant line drawn between 2 points on that function. Well, by now it should be clear to you that this equation here will give you that gradient. So if you have some point here x, this will be f of x. So the point here will be x comma f of x, and over here we have this point, and the first coordinate is x plus delta x, and the second coordinate will be f of x plus delta x. Alright, and so we find the change in the y and divide it by the change in the x. Some books, a lot of books now are calling this change here h. It doesn't matter. We can, for now we'll call it delta x. It's a change in x, as long as you know what it means. And so when you have this difference quotient here, then now you can find the gradient fairly easily. You just need to plug values in here. So let's take a function like this, 3x squared, and we want to find a difference quotient. And now this is stuff you saw in intermediate algebra and in college algebra, I believe. So it's the f of x plus delta x minus f of x. So x plus delta x, notice we simply replace x with x plus delta x. And then it's f of x, which is 3x squared, and then delta x. And then we just do some algebra here. We expand this. We get this expression. Notice x squared, 2 times the product of these items here, and then this term squared. And then we apply the distributive law. And then, of course, now we get that this minus this will give us 0, leaving us with just these two. And of course we can divide out by delta x. So delta x divided by delta x gives us 1, leaving us just 6x. And here we get delta x remaining here. So 6x plus 3 delta x. So now this allows us then to find the gradient at any point. I shouldn't say at any point. Of any between any 2 points on this function here. You just need to plug in the value of x and delta x, where x then is this value here, right? And so, for example, if you wanted to find the gradient of the secant line for these intervals, well, you just plug those values into this. So that would be 6 times 3 plus 3 times 5 minus 3 gives us 2. And if you just do that, you get these answers here. So you can check this yourself, right? So let's take a look at this one here, 3 and 4. If the interval runs from x equal 3 to x equal 4, notice that this would be 3 and that would be 4, no? Then delta x becomes 1, so that's 1, and then 6 times 3, 18. 18 plus 3, 21, right? Because 3 times 1 is 3, and then 6 3 is 18, 18 plus 3, 21, and so on. Let's take a little closer look at this using my favorite little app, GeoGebra. So I wrote a little, I put together a little thing here. I don't know how much of this you can see on the screen, but I think you can see enough, right? You can't see the entire app, but you see enough here. So what I have here is a little slider, and it's controlling the value of delta x. So notice this function is f of x equal 3x squared. I have 2 points here, and I want to see what the gradient of this of this secant line is going to be for various values of the coordinates of this point here. So I'm going to keep this point fixed at x equal 3, and of course then this becomes the point 327. So if you put 27 in here into this equation, sorry, if you put 3 into this equation, you get 27. Alright, and so we come over here and we have well, this point here is now 5.45. I can bring that point down. Notice I can bring the point down. For example, when delta x is 2, the point B is 5,75. Notice so the point B has an x coordinate of 5. And of course the gradient is going to be 24. So if you remember here, big mistake. If you remember here, when it was between 3 and 5, we have what, 24. So basically what I did is just use this equation here to do the calculations. And one very important concept then is to, or one important question is, well, as delta x gets smaller and smaller and smaller and approaches 0, what is the value of this gradient approaching? And so if you notice, I can make this value come all the way down to 0.01, and the gradient is 18.03. So what do you think would be the gradient of a line drawn tangent here? If you said 18, you would be correct. Notice if I try to make this 0, I get a big question mark here, because then you're getting a divide by 0. And so the question has always been, how can you get the instantaneous rate of change by using the secant line? Because you can't make delta x 0 simply and simply substitute in the equation. Right? So that's the question that we will be looking at here. Right? You can't take this equation here and just make delta x 0 because you can't divide by 0. But later on, as you can see here already, in fact, there is this little trick that we can do. And so we're not interested now in knowing exactly what the value of this equation will be when delta x is 0. We just want to know what value it's approaching as delta x approaches 0. All right. So hope that kind of hope that's clear. We'll be coming back to this again. So if you don't get it now, you'll get it the next time around. Now we switch our attention to some basic things that you need to know. You need to know that the area of a rectangle is the length times the width. The area of a triangle is 1/2 the base times the height. The area of a trapezoid is 1/2 times the average of the parallel sides times the perpendicular separation. So it's easier to memorize things this way than to just memorize 1/2 open parenthesis a plus b. That's not a good way, right? You remember what a trapezoid looks like. You know what their parallel sides. You know what the average is. In this case, right, you just add two things and divide by 2. And so it's the average of the parallel sides times the separation, and so you can remember this easily enough. So this will come up later on as we move on through this course. And so you look at a problem here, and we're going to look at a little application here. So you have a particle that's moving horizontally with a constant velocity of 8 meters per second. How far does it move in the time interval 0 to 6? Well, obviously, if something's traveling at 8 meters per second, that means it covers 8 meters every second, and assuming the velocity is constant. And so in 6 seconds, it should have traveled 48 meters. If you look at it graphically, you see that you have this constant velocity here that's represented by this horizontal line, and we want to find the distance traveled in 6 seconds between 0 and 6. Well, that's this interval here. And of course, if you find the area here, you get 48 meters. So this is very important, finding areas. And we'll be working, in a sense, with rectangles. So just make sure you know how to find the area of a rectangle. In this case, we have the motion of a particle that is described as we see here. So what's happening here? It's moving to the right, speeding up, then it travels at a constant speed, and then it begins slowing down, all the while moving to the right. So this particle is moving to the right all the time, speeding up, traveling at a constant speed, and then slowing down. And so we want to find the change in the particle's position in this time interval. Well, that's what we have here, from 0 to 6. And well, in this case, it's easy. We just find these areas here, and so the change in the position would be 6 to 4. So we have a trapezoid here. So this is a little formula for the trapezoid. We have a rectangle, and then we have another trapezoid here. So just make sure you know to do this, right? And so if you have a rate and you want to know the amount, you simply find the area, right? So the velocity is a rate. It's a rate at which the position is changing. You may not have seen this in intermediate algebra, or maybe even in college algebra. But it's something that we need to be familiar with. So Suppose you want to express the sum of integers from 6 to 24. Well, you're not going to want to write 6 plus 7 plus 8 plus 9 and so on. It could be worse, from 6 to a million. You don't want to do that. So we have these little operators here. And so this operator allows me then to express that summation, right? So this is called the summation side. It says basically add what? Well, these values, but from I equals 6 to I equal 24. So this is the first I, the second I, the third I, and so on. This I equals 6, I equals 7, I equals 8. So let's make sure you understand this little summation sign, right? Let's suppose you want to express the sum of even integers from 6 to 24. Again, you would not want to go 6 plus 8 plus 10 plus 12 plus 14, right? And so one way to do this would be to say 2i from I equal 3 to 12. Notice 2i initially is going to be what? Well, 2 times 3, and then it's going to be 2 times 4, and then it's going to be 2 times 5, all the way up until 2 times 12. And so that would give us 6 plus 8 plus 10 all the way up to 24. So this, again, it's about mathematics. Very often, you know, it's about communicating an idea, and we want to be able to carry out that communication effectively. In this case, we want to sum powers of 2 from 2 to the third to 2 to the 11th. So again, you could say 2 to the third plus 2 to the fourth plus 2 to the fifth plus 2 to the sixth. But with this now, we simply say 2 to the I, and this is saying then sum all these 2 to the i's, where I can run from what? 3 to 11. You can also do this to sum up like lists or part of lists. So for example, let's suppose you have a list here with arbitrary values, and you want to sum up all of them, 1, 2, 3, 4, 5, 6. Well, what you do is you say you want to sum from 1 to 6. Most of the time I prefer to write out literally explicitly, you know, I equal 1, but sometimes some authors don't bother to put I equal, because it's obvious, it's this I value that will be changing from 1 to 6. So this is saying add x1 plus x2 plus x3 all the way up to x6. And then of course, what is x1? x1 is 3, x2 is 6, x3 is 11. For those of you who have a little computer programming background, you probably prefer starting at 0, and that's fine, but for us, we'll just start at 1. You could also express subsequences here. So suppose I wanted to add just the first 3, I could just go, well, then I equal 1 to I equal 3. And of course, you could imagine that if you wanted to add every other one, you could play with this and figure out how to express that idea. Alright, so this video is coming in right under 15 minutes. So thanks for your attention. I hope you understand this, right? So go over this material and make sure you can do the assignment.